I would like to begin by saying that it's a great pleasure for me to give a talk at Gopal's Day, and I would like to thank the ICTS for making this event possible. I have had the pleasure and privilege of knowing Gopal Prasad and working with him on several research projects in the course of about 30 years. And today I'm going to tell you about our very first project, which was the congruence subgroup problem, and more precisely the computation of the metaplectic kernel. But first, please join me in wishing Gopal Prasad a very happy 75th birthday. The investigation into the congruence subgroup problem began back in the 19th century, but there are still important cases where the problem remains open today. I'm going to tell you about some of the available results, but also would like to refer you to our survey paper for more details. This paper is titled Developments on the congruence subgroup problem after the work of Bass, Milner, and Serre. And this article was published in volume 5 of Milner's collected works. I should point out that in this article, as well as in today's talk, we'll be concerned exclusively with the classical case of the congruence subgroup problem for S-arithmetic subgroups of algebraic groups. But nowadays, the congruence subgroup problem is being actively considered for the automorphism group of free groups, for the mapping class groups, and more generally for the automorphism groups of arbitrary finitely generated groups. Now, speaking about linear groups, given the commutative ring R, and its ideal A, one can consider the homomorphism of reduction modulo A. The kernel of this homomorphism is usually denoted like this, and is called the congruence subgroup. Of level A. More generally, given a subgroup gamma of G, L, and R, we define the congruent subgroup in gamma simply by taking the intersection of gamma with the congruent subgroup in G, L, and R. Of course, this is a normal subgroup of gamma. Moreover, in this talk, the ring R will almost exclusively be the ring of S integers in a global field and then, of course, for every non-zero ideal, the quotient is finite. Implying that, in fact, each congruent subgroup is a normal subgroup of finite index. Now, given this supply of normal subgroups of finite index that are naturally associated with the ideals in R, one is naturally led to consider the following question, which is known as the congruent subgroup problem. Does every normal subgroup of finite index contain a suitable congruent subgroup? Now, for the first time, this question was considered back in the 19th century for the group SL2Z, which of course is central to the theory of modular functions. And at that time, Keum and Klein discovered that the answer to the congruence subgroup problem in this case is negative in a very strong sense. The point here is that quotients modulo congruent subgroups have a very restricted structure. Namely, the quotient of SL2Z modulo the congruent subgroup of level M is of course isomorphic to SL2 over the finite ring Z mod MZ. But now, if M has the following prime factorization, then it follows from the Chinese remainder theorem that this quotient is actually isomorphic to the direct product of the following groups. So it follows that a quotient modular congruent subgroup has a composition series in which the successive sections are either cyclic groups of prime order or almost simple groups SL2 or Z or PZ. On the other hand, the quotient of SL2, Z modulo plus minus 1, is well known to be the following free product. Which implies that SL2Z can be mapped onto many finite simple groups that are different from the groups I listed above. And as a consequence, one obtains that the kernels of these homomorphisms do not contain any congruent subgroup, providing the negative answer. And while the description of quotients modular congruent subgroups can be extended, for example, to the group SL3Z pretty easily, the structure of this group is significantly more complicated than the structure of SL2Z, So it's not obvious how to map these groups on finite simple groups other than PSL2 of Z over PZ. So in this case, the congruent subgroup problem remained unresolved, at least in the 19th century. And in fact, there seems to be no evidence in the literature of any attempts to settle the congruent subgroup problem in this case. So probably the negative solution for SL2Z has a sort of discouraging and very lasting effect. Now the interest in the congruent subgroup problem redeveloped in the 1960s. First, independently, Bass, Lazard, and Sury, and also Mikhail, showed that for the group SL3Z, the answer to the congruent subgroup problem is actually yes. And I must say that their argument was quite elementary and didn't use any number theoretic techniques other than the Dirichlet's theorem on primes and arithmetic progression. So potentially this argument could have been found back in the 19th century. Next, a few years later, Bass, Milner, and Sury investigated the congruent subgroup problem for the groups SL and R, where n is at least 3, but now R is allowed to be the ring of integers in any number. And the result turned out to be quite surprising. So while, for example, for the group SL2 of Z adjoint the square root of 2, the answer to the congruent subgroup problem is still yes. SL3, sorry. But for the group SL3 of Z adjoint I, it already becomes negative. However, the reason why the congruent subgroup property fails in this case is different from the reason it fails for SL2Z. Namely, we know for a fact that the group SL3 of Z adjoint I does not have any finite single quotients different from PSL3 over appropriate finite fields. So morally this case is closer to the case of SL3Z, but the answer is still negative. Now, to describe what happens here in precise terms, we need to introduce the notion of the congruence kernel, which was proposed by Sury. First, we need to fix some notations that will be used throughout the talk. So we let G denote a linear algebraic group over a global field K. We let S denote a subset of the set V, sub V superscript K of all valuations of K. And we assume that S contains all Archimedean variations if K is a number field and is at least non-empty if K has positive characteristics. Although in principle S doesn't have to be finite. Then we let O sub S denote the ring of S integers in K. Next, we fix a faithful K-defined representation, and this allows us to talk unambiguously about the group of S integral points, which I will denote by gamma. It would simply be G intersects and moreover, for every ideal A in OS, we can introduce the corresponding congruence set. Next, we can introduce two topologies on gamma. First, the so-called S-arithmetic topology. It is compatible with the group structure of gamma and has a fundamental system of neighborhoods of the identity consisting of all normal subgroups of finite integers. So it's really the profinite topology of the group gamma. And we also have the so-called congruence topology. Here we have a fundamental system of neighborhoods of the identity consisting of all congruent subgroups. Clearly, the arithmetic topology is not weaker than the congruence topology. And in fact, the affirmative answer to the congruent subgroup problem is equivalent to the fact that these topologies are the same. Now, to measure the difference between these two topologies in the general case, we consider the corresponding completions. And in this case, the completions can be described in terms of inverse limits without using Cauchy sequences. The S-arithmetic completion is the inverse limit of really all finite quotients of gamma. And the congruence completion is the inverse limit of the quotients modulo all congruence subgroups. And again, since the arithmetic topology is not weaker than the congruence topology, there is a continuous homomorphism of topological groups. Which turns out to be surjective, and whose kernel is called the congruence kernel. And what easily shows that the two topologies coincide even only if the congruence kernel is trivial. So the affirmative answer to the congruence subgroup problem is equivalent to the triviality of the corresponding congruence kernel. Now, in the general case, the size of the congruence kernel characterizes the difference between these two topologies. In other words, it describes the deviation from the positive solution to the congruence subgroup problem. So, according to Sir, by the congruence subgroup problem, one should mean the problem of computation of the corresponding congruence kernel. Now let me show you what the congruence kernel is like in the examples we talked about earlier. The congruence kernel of the group SL to Z is known to be a free profile group of countable rank. So it's a very large group, which is consistent with the fact that the congruence subgroup property fails quite dramatically in this case. Now the congruence kernel for the group SLNZ, where n is at least 3, is of course trivial, as is the congruence kernel, for example, for the group SLN of Z adjoint the square root of 2. Now, what's the congruence kernel of the group SLN of Z box I? Well, as I told you earlier, the answer to the congruence subgroup problem in this case is no, which means that the congruence kernel is not trivial, but in fact, one can prove that in this case, it is the cyclic group of order 4. And now I would like to describe a general method for computing the congruence kernel, which will at least explain the results in parts B and C. First, one observes that both topologies can be extended from gamma to the group of rational points G of k. And in fact, this group admits completions with respect to these topologies, which will be denoted G hat and G bar. Again, for the same reason as above, since one topology is a priori stronger than the other, there is a continuous group homomorphism. Which turns out to be surjective, and whose kernel actually coincides with the congruence kernel defined earlier. So in particular, it's a profinite group. Thus, the congruence kernel, which I will denote simply by C, becomes part of the following exact sequence. Now, the description of C in terms of G hat and G bar, rather than in terms of gamma hat and gamma bar, has a number of advantages. One, it quickly leads us to the conclusion that the congruence kernel C is independent of the choice of the invariant. Second, this construction gives us an action of G of k on C. And in fact, in many cases, one can use the known facts about the structure of G of k to conclude that this action is actually trivial. Well, in this case, we say that our congruence kernel is central. And this really helps us to compute it eventually, so I will explain later. And three, in this case, we can actually identify the congruence completion. Okay, more precisely, the general case in the congruence subgroup problem can be reduced to the case where G is absolutely almost simple and simply connected. Moreover, we can assume, of course, that gamma is infinite. Otherwise, the answer to the congruence subgroup problem is clearly yes. Now, in this setup, the strong approximation theorem implies that the S-congruence completion can be identified naturally with the group of S-cells. And here I would like to point out that the strong approximation theorem for number fields was proved by Kneser and Platonov, and over global fields of positive characteristic was proved by Prasad and Margulis. And this brings us to the problem of studying the following topological extension. From now on, I will suppress S in the superscript. So, which is a topological extension of the Adel group by a profiling group. Another important property of this exact sequence is that simply by construction it splits over the group of rational points. And in fact is the universal sequence with these two properties. Now, in order to get information about C from this exact sequence, one uses duality. More precisely, we consider the initial segment of the Hochschild set spectral sequence of continuous homology with coefficients in the one-dimensional torus are C with trivial action. So, to keep my notation simple, I will write HI to denote simply the continuous homology with coefficients in R of C. Okay, here's the sequence that I need. And I will call this map phi and this map psi. Now, using the fact that our congruence sequence splits over the group G of K, and in fact is universal for this property, one shows that the image of psi coincides with so-called metaplectic kernel. which is defined to be the kernel of the restriction map. And this brings us to the following exact sequence. 1 followed by the co-kernel of phi. And we have this middle term. Followed by the metacritic kernel. I will give you a precise description of the metacritic kernel in the end of this talk, but for now I would like to talk about the co-kernel. Now, it can be described as the dual of the following quotient. Of course, as always, this denotes the commutative subgroup of G of k, and the bar denotes the closure in the S-arithmetic topology. Now, in many cases, it is known that G of k is an almost simple abstract group, which means that it does not have any non-trivial, any proper non-central normal subgroups. And of course, if this is the case, then G of k is perfect. Which implies that the co-kernel actually vanishes. And this is always the case if G is k isotropic, meaning it has positive relative rank, which follows from the positive solution of the Lazard problem over global fields. And here I would like to mention Prasad's contributions to the Lazard problem. Now, in a joint paper with Raghunathan, they reduced the general case of k isotropic groups of arbitrary rank to the case of relative rank 1. And this reduction quickly gives the affirmative answer to the Lazard problem over local fields and reduces the case of global fields to the verification of a small number of cases. And one of these cases, namely the trilateral forms of type D4, was considered by Prasad himself. What about the anisotropic case? Then the normal subgroup structure of G of k is controlled by a conjecture due to Platonov and Margulis, which we call conjecture MP. Today I'm not going to give you the technical statement of this conjecture, but what it implies is that if G is not of type AM, then again G does not have any proper normal subgroup, so it's perfect. So the co-kernel again vanishes. Now, if G is of type AM, then we may have that G is not perfect. But then conjecture MP tells us that the commutative subgroup must be closed in the S arithmetic topology, provided that S does not contain any anisotropic non-Archimedean places, which we usually assume. So in this case, again, the co-kernel is going to vanish. Well, this is known to be the case for all inner forms of type AN, but the question is still open for outer forms. So the bottom line is that conjecturally, namely assuming the truth of conjecture MP, we can say that the co-kernel must always be trivial, which is known to be the case in many, many cases. So from now on, let's indeed assume that the co-kernel is trivial. So in this case, so our exact sequence gives us the following isomorphism. Now, in practically all cases where C is known to be finite, its computation has been carried out following in the following two steps. Step 1. We prove that C is central. And E is contained in the center of the S arithmetic completion. Now, in some cases, the proof of centrality is easy. In other cases, it's less easy. And in yet other cases, it remains an open problem. But again, if we have centrality, then the boxed formula actually tells me that H1 of C which is really the Pontryagin dual of C, is isomorphic to the metaphysitic kernel. So in order to determine C, as step 2, one computes the metaphysitic kernel. While there are still important cases where the centrality of C is expected but has not been established yet, the metaplectic kernel has been computed precisely in all cases relevant for the congruent subgroup problem. So the final result was obtained in our paper with Prasad. Titled Computation of the metaplectic kernel. But it was preceded by a series of papers by Prasad and Raghunathan, where they have carried out completely the local computations and also gave global computations in the case where the group G is K isotropic. Among other important contributions to the computation of the metaplectic kernel, I would like to mention important papers by Matsumoto, Moore, and Theodore. So now let me show you the statement of our theorem. So let G, K, S be as above, meaning that G is absolutely almost simple, simply connected, K is a global field, and S is the appropriate set of places of that field. Then the metaplectic kernel is isomorphic to a subgroup of with K, which is the group of all roots of unity in K. In particular, the metaplectic kernel is always finite, and therefore the congruence kernel is finite once it is central. And part B is that if S contains a place V0, which is either non-Archimedean and G is KV0 isotropic, or is real and the group GKV0 is not topologically simply connected, then the metaplectic kernel is trivial. I guess some remarks are in order. So part A tells us that if the congruence kernel is central, then it's automatically finite. Conversely, if it is finite, and we assume the truth of conjecture MP, then it is central. So centrality is essentially equivalent to the finiteness of the congruence kernel. So A and B basically tell us that the metaplectic kernel is always in between the group of all roots of unity and the trivial group. But if we assume in addition that S does not contain any anisotropic non-Archimedean places, we can make this dichotomy even sharper. So in this case, the metaplectic kernel is either one or the other. And in fact, it's trivial only in the precisely the situation described in part B. Now, in fact, in our paper, we've also considered the case where S is empty. And this case is important for the theory of automorphic forms. What we show in this case is that then the metaplectic kernel is always the group of all roots of unity in K. And now, to illustrate this theorem, let me show you how it explains the results I mentioned earlier. Let's consider the group G, S, L, N, where N is at least 3. In this case, one shows that the congruence kernel is always central. It's a really easy argument, and I really have it in my notes that I posted on the website, but I don't have the time to put it up on the blackboard. Okay. Let's see what happens for the group SL and Z. Then, of course, the relevant field is the field of all rationals. S consists of a single real place. Now, it's well known that the topological fundamental group of SLN R is Z mod 2Z. So the group SLNR is not simply connected. So by part B of the theorem, we conclude that the metaplectic kernel is trivial, so the congruence kernel is also trivial, which is consistent with what I said before. Now, basically the same argument applies to the group SLN of Z box the square root of 2. Here the relevant field is K. K is Q adjoining the square root of 2. And the set S consists of 2 real places. Both places are real, and the group SLNR is not simply connected, so we conclude that the metaplectic kernel is trivial in this case. Finally, let me show you what happens with the group SLN of Z box I. So in this case, the relevant field is Q adjoint I. Now S consists of a single complex place. So this situation doesn't fit into B. So therefore, we conclude that the metaphysical kernel is isomorphic to the group of all roots of unity in K, which is the cyclic group of order 4. So explaining our previous computations. Now, I must say that the proof of this theorem involves many ingredients and also requires a case-by-case analysis. But one of the most important ingredients is the local computations of Prasad and Raghunathan, which I will summarize in the following theorem. So let K script be a non-Archimedean local field. And G be an absolutely, G script be an absolutely almost simple, simply connected K group. Then H2 P of K is always isomorphic to the group of all roots of unity in K. Now, the original paper of Prasad and Raghunathan contained little ambiguity, so the result was it's either this group or this group divided by plus minus 1, but this ambiguity was later removed by Prasad. And in the conclusion, I would like to show you one result that for the case where the congruence kernel is actually infinite. So let's return to the group SL2Z that we discussed earlier. As I told you, in this case, the congruence kernel is the free profinite group of countable rank Nevertheless, we were able to show with Prasad that as a normal subgroup of G hat, C is generated by a single element. And we have similar results for other isotropic rank 1 groups. Besides, we can actually give this element pretty much explicitly. So that's all the time I have today. So I would like to conclude the lecture by wishing Gopal a happy 75th birthday once again. Thank you very much for your attention.